The two things that we will see today is two extension of expanded decomposition that we look at last lecture. The first one is dynamic version. Okay, so what is this? Okay. The setting is that you have a graph. Maybe I draw it here. You have a graph, G, okay, and a parameter phi, just like before, just like in previous class. And the idea here is that I still want to find a phi expanded decomposition for G, okay. But now there is something that is more complex from last time. That is, there is a user, and this user can update the input somehow. Okay. What can the user update? So there are two things. The set D. You should think of this set D for deletion, the edge set that the user keep deleting. Like this set can grow, so it means that there are more and more edge that got deleted one at a time. Okay. And also there is this node weighting A. Okay. Previously the node weighting A is fixed. It's just some node weighting, like some indicator vector or something. But now this node weighting can be updated too. So for every node V, it can increase. Like the user can ask you to like set AV to be AV plus 2 or something. Yeah. So this is a two kind of updates that the user can do. Okay. And the idea is that, like the goal is that after these updates, we kind of want to get a new expanded decomposition at all time. Okay. So what do we want exactly? We want to show this thing, this subroutine, okay, that get the graph, a parameter phi, and this set, this A and D. This A and D is like keep updating, okay. And we want to maintain an incremental set C, meaning that this set C only grows as well. Okay. Okay. And then the set C should be what? Like I require that the set C always contain D. So think of C as the thing that you cut out of a graph, right? And then like you ask yourself to cut the thing in D too. So that's why I said that D, you think of D as a deleted edge. So you need to cut things that, like you need to cut things from the graph, and the thing that you cut contain D. Okay. And now what we want from the set C here, it's just like before, just like in expanded decomposition. We need that after removing C, A is now expanding in G minus C, expanding. Yeah. Okay. Right. And another thing that we want is that the number of edges that we remove from the graph, addition to the thing that user remove. Okay, this set should be something like of size phi A. So if you think of D as empty set, then this and if A is just a static set, this is just like an expanded decomposition for A, like in previous class. Okay. Okay. So that's the goal. Question about what we want. Yeah. Okay.
Did you say A can only increase?
A can only increase. Yeah. ครับว่า
Does C also contain D within itself, or are they like two separate things? I guess.
C will always contain D. Yeah.
Then why do we need the requirement that C minus D is less? Like,
C.
is it just the edges that like we choose to delete
Oh,
to do the expansion, or?
So because like D could be really big. And like if I just say that like so how should I say this? So D actually could be much bigger than this thing. But what we want to say is that if D is so much bigger than this, then there is no way that C itself is smaller than this one. Right? Because C needs to contain D. But to be able to say something meaningful, we can still say that, okay, D might be big, but the thing that is kind of in addition that we delete more than D is not too big.
Okay.
Yeah. Okay. Okay. So we want to do this at all time. Okay. And like, so one way to solve, not quite solve this, is that whenever A is updated and D is updated, you just look at the graph G minus D and just compute expanded decomposition from scratch. You will get this thing. But that would not work because if you solve everything from scratch, your solution might not only grow. Okay, like I want like my solution to grow like monotonically. Okay. Question about this? Okay, so now we're gonna try to prove this. Okay. And any idea actually?
Can we just do expanded decomposition in G minus C each time? And then
like in G minus C?
Or G minus, yeah. Like before, like every time that there's an update, like just start with like our current, like all of the edges we're currently cutting.
Exactly.
As like the initial thing, and then just look for sparse cuts in there.
Good. You just said that, okay, like computer expanded decomposition, we get C, and that is expanded decomposition, and now just wait for the next update. Maybe you delete something more, you grow A, and then just do expanded decomposition in G minus C. Like continue doing that. Yeah, that's the idea basically. So okay. So the idea is just this. Okay. This is just I repeat the algorithm from last time, which is just start from C equal empty set, and then if A is not expanding, it means that there must exist a 5 sparse cut. Then cut it, like there is an exists 5 sparse cut like this, right? And then you cut it, and at some point you return your expanded decomposition. And then now the user can update things. So let's say that they update D. What we do is just include D into your deleted set. Okay. And then just look again, just check again if A is expanding in our currency. And if so, you just check if there is a sparse cut. And keep cutting until there is nothing to cut more. Similar for A, right? if A is updated, then just update it and check for the new sparse cut. So the idea is just whatever happened, just check if there is a new sparse cut or not. If there is a new sparse cut it and continue. Okay. So with this, it means what? It means that our set C will be incremental set. It only grows. Okay. And obviously, once we terminate at any point of time, A will be phi expanding in G minus C, and C contains D. So what remains is just to show that like the size of C is small. Like we now want to bound C minus D to be at most this much, right? Okay. So I let you try to do this for like 10 minutes. Yeah.
It must be like sparse cut.
Yeah, maybe I still put it here. So bow, C minus D. So note that when you try to bound this, you know for sure that you cannot bound the C only, because D could be big, right? Just need to say that the thing that you delete in addition to D is small. Anyone have some suggestion how to proceed on this? Yep.
Sorry, is this the lecture 2 notes?
This is lecture 3.
Oh, lecture 3 notes, okay.
Yeah.
So the discussions count as a lecture, right, in the numbering?
Yeah.
Okay.
Sometimes, I guess, yeah.
We maybe try to use like the bank account method. Like,
Still bank account method, yeah.
Maybe we like give each node like in lecture like 5 times A of V log n dollars.
Mm-hmm.
And then for every edge that was deleted in C, maybe we would spend $2, and then for each edge deleted from D, we spend $1.
Mm-hmm.
So then like the size of C would be less than or equal to phi, the size of A log n, and then
1 second, you say, like, in the beginning, all nodes, like for all V, give to V this much money,
phi, yeah, A of V log n dollars.
right? So it means that the total money is at most something like phi A
Log n.
log in, right? Yeah. But now, okay, if we have this much money, and if whenever you delete something in D, and you pay using this money, then it means that you cannot delete more than this much.
Oh, well, what if we give like 2 times that to each node?
If you give 2 times this,
Yeah.
then it means that we cannot delete more than this much.
'Cause
Like,
we could have like O of
we
n
could
squared
really like
patients.
delete a lot of things.
Oh yeah.
Yeah. So the idea should be that we don't want to pay anything when we delete from D, actually.
Because D can be really big, right?
D can be really big. Any more ideas? Okay. Should I actually proceed, or do you want some more time? What do you think? What do you think? Proceed? Okay. More time? Okay. A bit more time. A bit more time. Yeah. Yeah, by the way, I kind of assume lecture 2, so if you have a look at that, you're good,
I
right?
understand the problem.
Okay, great, great, yeah. If there's some notation that doesn't make sense, just ask, yeah. Okay, let me actually proceed actually. So the goal is that we want to bound this thing, right? And it means that, so you just need to ask yourself, like, when does this quantity increase? Right? Just increase when you do this. When you find a sparse cut and you cut it, add this sparse cut into your set C. Okay? This doesn't count. Like this is when both D and C increase. So you just need to say that, okay, whenever you find a new sparse cut, you have some money to pay for the new cut edges. Okay? And then the idea is basically the same. Like the idea is that if you find a new sparse cut, let's say at some point, let's say there is some cut that you have found so far, and there is a new sparse cut that you have found. Just try to use money on the node weighting to pay for the sparse cut. And the idea is that if you start with some money on each node weighting like this, you should be able to use the money on this node to pay for the cut because the cut is sparse. The cut is sparse, meaning that the number of edges crossing the cut is kind of small compared to the node weighting. So it's really kind of almost the same proof. Okay. So what I want to say is, let's say that at any time t, okay, we want to say that C at time t minus D at times t is, let's say, small, like at log n. Okay. So the plan is similar to class. Give this much money to every node. Okay.
We're just looking at some iteration of the while loop.
Yeah. Look at this t. No, just think of this t as the time step from the user perspective.
Okay.
So, once the user update, given with the first update, then it's become A1. The second update, it become A2. Okay. Then, so we still want to, yeah. You just said that we want to pay $1 for every edge in C minus D without that. Which is, this is just a guide that you add to see when there is a sparse cut. Okay, if you can do this, then you would be done. Okay, like C at time t and D at time t is at most this. Okay, and so how would you pay it? The same way. When you get a new sparse cut, like here, you find a new sparse cut, then every node on the smaller side, let's say like every node on the smaller side here, pay this much. and this gives the total budget of this, at least. Okay, because the total money that we get would be 5 AS, okay, which is at least this much. But the cost is just the number of edges along the sparse cut. So the cost is at most the budget, and the reason is that S is 5 sparse before time t. So what do I mean by this? So I mean that like what I mean is that I kind of analyze, like, suppose that this is my goal, right? I want to analyze to bound this at time t, okay? But what I'm gonna do is just, I imagine that I run my algorithm from scratch, from the beginning. And it means that like this, so how do I say this? Like think like this is a timeline starting from time 0, time 1, up to time t. Okay. And at time 0, before any updates, I might find like a bunch of sparse cut here. After the next update, when I delete some more edge or I increase A, there's new sparse cut. And after this update, there is newer and newer sparse cut. You know what I mean? So I just look at this time, and I imagine that we keep finding sparse cut from time 0 up to this time. So the sparse cut that we found, the sparse cut S here, is a sparse cut at some point before time t. Okay. And like, so we know that this is sparse with respect to A at some point before time t. But this is less than this one because A only increased. Yeah. So it just means that we get like the budget that we have is enough to pay for the cost. Yeah.
So we're basically using like whenever the A is at t just as a way to bound kind of the A at any point in time.
Yeah.
That's what the highlighted.
Right. Like this is also a reason why I need that A only increase. Like this wouldn't be true if A could decrease. Okay. So this is a bit subtle. Yeah. But now like so here we just have that like at any point of time when we find a new sparse cut, we can use money at time t to pay for the cut here. Like I just think like I have the money is defined at time t, and I use it to pay for all the sparse cut that I have found in all the at every time step in the past. Okay. And now, okay, so we have the money to pay for each sparse cut, and we know that each vertex will have money at least 0 at all time, just because at every time that it pays something, it is on the smaller side. It pays this much, but it is on the smaller side. But it can be on the smaller side at most log n times. Yeah.
So another way of looking at that is that sparse cut or cuts that were sparse at times before t are still sparse cuts
Yeah.
time t.
Exactly. Yeah, the cut that was sparse before time t must be sparse at time t as well. Yeah. Because A only increase. Okay. So this is kind of, that's it. Like this is kind of just some exercise, but we will actually use this on Tuesday. Yeah. Okay. Or later, yeah. Okay. Next version of expanded decomposition. Okay. So we call it boundary linked. Okay. The boundary linked version. Okay. And what is this version say? What does it say? It says that actually, let me try to find the slides that is. I had a slide that is better than this one. One sec. Shoot. Okay, good. Okay, this is just from last time. This is just expanded decomposition, normal one. Now, here is the boundary link version. So what do I mean here? Okay. I mean that it's version that, okay, you find C, that is also basically the same size like before. There is some factor 2, it doesn't matter. But now, I need that, not just that A is expanding in G minus C, but A plus degree of C is expanding in G minus C. Okay, so what does it mean? Like, it means that if you look at, like previously, you have that when you look at any component, right? You, after deleting C, you look at any component here, then A inside here is expanding in the component. That's what happened before. But now we say that even after adding this node weighting, meaning that look at the endpoint of the cut. Like, think of the endpoint of the cut as another node weighting that you care about too. A inside together with the boundary, they are expanding together inside this component. Okay, so it means that previously there could be actually some really sparse cut, maybe here, right? There could be sparse cut here. It doesn't matter for A because A is still well connected to each other. But like A could be separate easily from the boundary. But now, like if I want that A plus degree C is expanding, it means that now you cannot have really sparse cut here anymore. Okay. So, yeah. If you look into each component U, A inside U, this part, together with the battery of U. This is like to denote the battery of U. Okay, like the end point of the battery. This thing together, they are expanding. Question about the statement. Yeah.
So the boundary of U is defined as like the vertices are adjacent to the edges in C.
So this thing, it kind of means like maybe think of it as a node weighting of degree out like on the cut, yeah. Yeah. So this is just maybe just the cut intersect U. Yeah. Just the same thing here. Yeah. But intersect U. Okay. So I need you to understand the intuitive definition of this statement before we try to prove it. Questions? Yeah.
Why do we impose the condition on phi? Like,
Very good. So it's just because I can only prove this. Yeah.
oh,
I don't think we can do it that like when phi is big. Yeah. Bigger than this one. More questions? Yeah.
so the degree C, does that just look at the endpoints of the
Oh, very good.
edges which
Yeah,
are-
yeah. This is yeah. So very good. So for any like edge set, yeah, then the degree, the node weighting of that edge set is just defined to be like the total capacity of F edges incident to V. Or in this case, if you think of unit capacity graph, then just count the number of edges from F
Oh.
incident to V. So it means like if this guy would have node weighting 2 because it has this edge and this edge. This one, the node weighting on here is 1.
Makes sense. Okay.
Okay. All right. Okay, now I'm gonna proceed now, right? Okay. And 1 second. Let me see if there is. Wait. Yeah. And now, actually what we can prove is this version. Like, you can think of, it doesn't just need to be a new, like A plus degree C. You can just say that like this is some beta and think of beta as something more than 1. Okay. So maybe you should think of phi as something like more like think of phi as maybe like 1 over log to the 100, like small like 1 over large polylog. Okay. But think of beta as this thing. Okay. Okay. So beta is if this is like 1 over log to the 100, then beta is basically log to the 100, log to the 99. Yeah. Okay. So now think of beta as something more than 1. And I now just say that we can actually find this expanded decomposition such that it's very bodily linked. So this guy is like you put a lot of multiplier to the boundary, and it's still expanding here. Okay. Okay. It's just like before, but beta, you think of beta as something big, bigger than 1. Okay. So the way you think about it is like A here, the A inside the component is okay, it's just phi expanding, because like if this whole thing is phi expanding, then without this thing, A is phi expanding too. So this is just phi expanding. But what you know more is that the boundary is going to be phi over beta expanding, which is much better than phi expanding. Why is that? Well, because beta times boundary, or just think of this as degree C intersect U, right? Yeah, that's what I mean. This thing is phi expanding in GU. If this thing is phi expanding in GU, like if 10 times this is phi expanding, then it means that this thing only would be wait, sorry. This should multiply. Yeah. So if this is phi expanding, then it means that this without beta is phi times beta expanding, right? Like you scale down the node weighting, it means that it's easier to be expanding. Okay. So like this boundary is like close to 1 expanding, although like the A inside is like not so close to 1 expanding. So boundary is even more expanding than A. That's how you should think about it. Okay. If you set a parameter like this, and this is how we're going to use it at some point. Okay, let's try to prove this. Okay. Yeah. So the boundary is much more expanding. Okay. Good. So the algorithm, like when we don't care much about running time, the algorithm is just this. It's always the same. Just very simple. So how? Well, just say that okay. We used to want that A is expanding. Now we just say that we care about A plus beta. So let's say A prime is A plus beta. Just check that A prime is expanding or not. If not, fire sparse cut. Then cut it and keep fighting sparse cut until you cannot find it. After you cannot find it, then A is expanding in G minus C after you're removing all the sparse cut. Okay, so this is clear that once you are done, then A prime would be expanding in G minus C, which means that A plus beta degree is expanding. So this is clear. There's nothing to do. The question is how to bound the size of C again. Okay. right. And here's a plan. Okay. The plan is going to be quite similar. Okay. So you just have some initial money to each node again. This much. Now I have a factor 2, but it's doesn't matter too much. Okay. And without debt, we're just gonna say the same, that whenever we find a new cut edge, we pay $1. And if we do this, it means that if we can do this without debt, using only the money from the beginning here, then it means that the total number of cut edges is at most the total initial money. So this is the same. Okay. But now there is new thing. Okay. The new thing is that you see, whenever we like maybe whenever we find a cut, right? You cannot put new node weighting. So the node weighting A kind of keep growing actually. When you find a new cut, there are new node weighting. Okay. So but we kind of but the initial money is just at A. But there are new node that has node weighting. So what I want is that for every A prime vertex, so the vertex that are in the new node weighting A prime, it should have some money too. And how much? Is this much. Which is kind of makes sense. Like this is just kind of the same thing here, but just make A to be A prime. And the log factor here also makes sense because you just want it to get like a log factor of the size of the component that contains the node V. So for example, if you have a graph and you have like some sparse cut already, and let's say you look at this component, and then like if you want to put money, initialize the money on this node, the log factor that like from this node perspective, it's just a node inside this graph of size u, right? So the log factor here should be just depends on the component that contains this node. Yeah. Okay.
And is the size, I guess UV, is that the smaller component that's left after the cut, or?
It could be big. Like if V is here, then UV would be big. Okay. But if V is here, then UV would be smaller. So if V is on the larger side, then UV is big. Yeah. Okay. So I'm gonna maintain this invariant. Okay. And now let's see that this is, I can just use this initial money to both pay for the cut and to pay for like the new node weighting, right? Like whenever there is a new node weighting, like new edge on the boundary, that give kind of, it increase the node weighting, I need to pay for it too. Okay. But this initial money is just gonna be enough. Okay, let's see why. Okay. So I have a new cut, okay? And I just do the same thing. Every node that is in, like, that has some money in A prime, okay? Just pay this, just like before. So the budget that we get is this much. This is with A prime. Okay. And why do I know that I can pay this much because of the invariant, right? the invariant is that every node on A prime has some money. Not just the node from the initial A. Every node in A prime has some money. So it can pay this much. Okay. So now I get this budget. Okay. And now let's analyze the cost. The cost, I claim that it's going to be total of this. Why is that? Well, first, there are some new cut edges. This is what I need to pay for. It's just this much. Okay. That's one term in here. Okay. But another thing that we need to pay for is just the new guy in node weighting. So I find a cut here. Now, like there are cut edges. This guy need to get some new node weighting, meaning that we need to pay money for it to maintain the invariant. Right? The invariant says that every node in A prime need to have some money. So how much do I need to pay? Well, like I just look at the total node in, let's call this A prime new, the guy that I add to A prime. Okay. Every node need to have this much money, like 2 times 5 times the A prime new of that node times log U. Log U, why? Like this is a component U. So every node, and let's say this is like, actually every node here need to have like need to have like 2 phi A prime V times log S. This node need to have 2 phi A prime V times log U minus S. Right? But I even just pay this much. It's more than both sides. Okay. Okay. So the size of A prime is what? A prime new is just a cut size times 2 because each edge has 2 endpoints, and times beta because we scale up the node weighting there by beta. Okay. I need beta to be this much. Like this is like from the assumption that beta is not too big, and then you just multiply this thing together. You get that this is at most this much. Make sense? So like the total cost here to pay for the new node weighting is still at most the cut size. So in total, you pay for the real cost here, which is the cut size, and pay for the invariant, which is another cut size. So in total, it's just 2 times this thing. So it means that, okay, this is a cost, this is the budget, but again, we have that the cost is at most a budget. Why? Because we cut along sparse cut. So this is at most this. It's a sparse cut with respect to A prime. Again, note that this is sparse cut with respect to A prime, not A. But it's okay.